Hey everyone, welcome to homework 3.10. Today we are looking at the average rate of change over periods of time. And so I'm going to go over the homework first, and then I will go back and go over the last bits of the classwork for anyone that needs it. So let's start by looking at this problem review. Now this is asking you to go ahead and look at very specific intervals of time, plug them into this equation, and determine which interval has the greatest average rate of change. Now, just looking at this is a growth function, which means that over time, this function is going to increase. And always with growth functions, the greatest increase happens at the end or towards the end, the later values. The earlier values are slowly creeping up and increasing little by little. So just in looking at A and B where we have negatives, we know that those numbers we're going to be looking at much smaller numbers and therefore much smaller increases. But just to show you how we could also calculate that, we would be looking at, remember the later value was first, so 3 to the negative second power minus 3 to the negative fifth power over negative 2 minus negative 5. All right, so 3 to the negative second power is 1/9. So that's going to be 1/9 minus 1 over 3 to the fifth power, which if you use your calculator, you'll see that 3 to the fifth power gives you 243. All over negative 2 minus a negative 5 becomes negative 2 plus 5, which is divided by 3. So looking in that, right, you're subtracting a very small fraction from another fraction and then dividing by 3, you know that this number is going to be very small. Well, if you want to go ahead and do that, 1 divided by 9, and let me show you in the calculator itself. So let's get out of that. Right, so let's say we are using math and we're using fraction, and oops, that's actually not what I meant to do. So if we do 1 divided by 9 minus 1 divided by 243, we get a very small number, and then we are going to divide by 3, and we get 0.035. So this is a very small rate of change in the beginning, right? It's an increase of 0.035. It's a pretty small amount. Now, similarly, if we plug in 3 to the 0th power minus 3 to the negative first power all over 0 minus a negative 1 is just going to be 0 plus 1, or 1. 3 to the 0th power is 1, minus 3 to the negative first power is 1/3. That should be minus, my computer's being a little slow. Okay, divided by 1, which is going to be 1 minus 1/3, which is 2/3. And so this is also pretty small, and it's 0.66. Still looking at a fraction or a decimal. Then if we take a look at the next group of values, this is looking over a larger interval of 0 to 5. And if we calculate that, we will put in 3 to the fifth power minus 3 to the 0th power over 5 minus 0. And remember, we're placing the x here in our y values. And so 3 to the fifth power we know is 243, minus 3 to the 0th power is just 1 over 5. And so when you do that, you're going to get, let's see, 243 minus 1, and then divided by 5 gives us 48.4. So this one has a value of 48.4. But then we need to look at the last interval here. And so if instead we change these values, let's see what we get here, and we say 3 to the fifth power minus 3 to the third power over 5 minus 3 is 2. We will again have 243 minus 3 to the third power is 27 all over 2. So 243 minus 27 divided by 2 gives us 108. And so our greatest average rate of change is going to be from 3 to 5, because that is right later on in this example, that increase is happening even at an even greater and faster rate towards the end. All right, so let's look at the problems from this lesson. A store receives 2,000 decks of popular trading cards. The number of decks of cards is a function d of the number of days t since the shipment arrived. So as they sell them, right, the number that they have is decreasing, and this is the table of values. So it says calculate the average rate of change for the following intervals. So 0 to 5. So we're looking here. And so again, we're going to use our formula f of b minus f of a over b minus a, with b representing the later value. So 1283 minus 2000 over 5 minus 0, which is 5. So it's a period of 5 days. And then 1283 minus 2000, we're going to get a negative number in this case. Negative 717 divided by 5. And so here, it's important that you know what this means, right? So 717 divided by 5, which is going to be negative 143.4. So you would say per day, the books are decreasing by 100, not books. The decks are decreasing by 143.4 decks per day. And then from day 15 to 20, so now we're looking here, we're still looking at 5 days, right? A difference of 5 days there. But now we're looking at 338 minus 528. And so we'll still get a negative number because it is decreasing. 338 minus is negative 190 divided by 5, which will be negative 38. So in the first 5 days, it's decreasing by 143 per day, but in the last 5 days, or between days 15 and 20, it's decreasing by 38, which means our sales are faster at the beginning. When something is just released, it's selling faster, and then over time, it sells less and less each day. So that makes sense. Now notice that in the original, the first problem we looked at a growth model. And so in that growth model, that growth happened at a much faster rate later. However, in a decay model, the greatest change or the greatest decay is at the beginning, which we see here with 143 compared with 38, when we're changing a little bit less at a slower pace later on. All right, number 2, a study was conducted to analyze the effects of a deer population in a particular area. Let f be an exponential function that gives a population of deer t years after the study began. Select all statements that must be true. So if we're looking at an exponential function and we have this information, which of these statements must be true? So b is greater than 1. Well, if it is increasing, then that means our factor does need to be greater than 1. That also means it can't be less than 1. The average rate of change from 0 to 5 is less than the average rate of change from 10 to 15. Yes, because this is an increasing, a growth model, right? Our greatest growth is going to be later, and so then this is true. That means that the opposite is false. And then a is greater than 0. So a is our initial amount. Remember, that's the original amount. And that does need to be greater than 0 for us to make this work. Otherwise, we would be multiplying 0 times whatever would still be 0. And we do know that the population is increasing. All right, number 3, function f models the population in thousands of a city t years after 1930. The average rate of change from 0 to 70 is approximately 14,000 people per year. So if we look at these years from 1930 to 2000, the change, if we were to calculate that average, would be 14,000 people per year. It says, is this value a good way to describe the population change of the city over that time period? So for 70 years. No, because notice at the beginning, the population is changing much less than 14,000. And then at the end, we're looking at pretty large leaps of over 300,000 people changing. And so then at the end, it is increasing by much more. So 14,000 is the average, right? If we were to draw a line from here to here, it's the slope of that line, but it is not showing us per year a good representation at the beginning and then a good representation at the end. All right, so the function f gives the number of copies a book sold W weeks after it was published. This is the equation. It says select all domains for which the average rate of change could be a good measure of the number of books sold. So remember when I told you in our notes today that when we're looking at when it could be a good measure, it's only on very small increments, right? And so looking at this, B would be absolutely not, because that's a pretty large range. C is maybe, right? That's only 2 weeks we're looking at. D is 5 weeks. That's pretty significant. And E is 10 weeks. So that's also a pretty large range there. And so I would probably only say A or C because they're only looking at 2 weeks in that range. If we were to calculate the average change for those 2 weeks, that would be a pretty accurate measurement. All right, number 5 says the graph shows a bacteria population decreasing exponentially over time. So the graph we'll say is A, and then this equation B is our second graph, or our second situation. So in this case, the population remaining, right, our factor is 2/3. We're losing 1/3 of the population each time, but we're keeping 2/3, okay? So I'm just going to put a little note here, losing 1/3 of the population. And then in our graph here, if we look at this, our incremental or I'm blanking on the word that I want to use. But our points that are exactly one after another, we're starting at 250, and then at 1 hour, we're looking at 150. So if we want to find our factor here, we're going to go ahead and say 150 divided by 250, our later value over our earlier value. And when you do that, you will get 0.6. So this means for this population on the graph, I'm losing 0.4 of my population each time and retaining 0.6. So here, if I'm losing 1/3, that's losing 0.33333 and retaining 0.6666. And so this would mean that the graph is decaying more quickly because our factor is smaller, which means we're retaining less of what we are starting with. All right. Let's look at the next one. Oh, consecutive. That's the word I was looking at. Consecutive hours. Came to me now. All right. Number 6. A moth population P is modeled by the equation 500,000 times 1/2 to the power of W, where W is the number of weeks since the population was first measured. What was the moth population when it was first measured? So that would be when the weeks are 0, and so that would be 500,000. That is our starting amount. The moth population after 1 week would be half of 500,000, so that would be 250,000. And then if we're looking at 1.5 weeks, well, let's go ahead and take a look at our calculator here. So we're going to have 500,000 times 0.5 to the power of 1.5. And for this, we get 176,776. So let's shift back. 176,776, I think is what I recorded, for 1.5 weeks. And that makes sense. It's not going to be half of this yet because that will happen after 2 weeks. It says use technology to graph the population and find out when it falls below 10,000. So let's do that. That's why I have this calculator app open today. So we have 500,000 times 0.5, or 1/2, to the power of x. And let's go ahead and graph that. So we obviously cannot see this, which would mean that we would need to zoom out a bit. Let's go ahead and do that. And now we can see this graph here. And if we want to see where it falls below 10,000, remember a good place to look is the table. So second button and the table. And notice now we can scroll down and look to when is it going to be less than 10,000. And in this case, we're looking at between 5 and 6 weeks. At 5 weeks, we're still at 15,000, but at 6 weeks, we're at 7,000. So I would say between 5 and 6 weeks. And if you wanted to try and get a little bit more specific, we can go back to this graph. And let me go ahead and press trace. Let's see where our point is. There we go. Okay. So here we're looking at, so this is x is 14. We need to go back quite a bit here to, we said between 5 and 6. So let's try to look. So at 6.6, we're at 4,900. At 6, we're at 7,000. Here we go. At 5.4, we're at around 11,000. So we can estimate around 5.5-ish, right? That it's going to fall below that 10,000 mark. All right, our last question here is a graph of Hans' distance from home as he drives. Identify the intercepts of the graph and explain what they mean. So our first intercept is 0, 10. That is our vertical intercept or your y-intercept. And that means at 0 minutes, he is 10 miles from home. And then our second one, or our horizontal intercept, is 10, 0. And this means after 10 minutes, he is 0 miles from home. Or in other words, he's home, right? All right, your code word for today will be Fiji. Fiji is your code word for today, so remember, put that at the very top of your classwork because that will tell me that you have listened to everything. I'm going to go ahead and go now back to the last part of the classwork, these points right here, to show you how to do these and make sure you have some additional help here. So we're looking at this interval range. For all of these, our denominator is going to be 5 minus 2 or 3, right? We know that because that is our inputs here. Then our outputs are going to be what we get when we plug these numbers in. So if I plug in 5 for x, I will get 11. If I plug in 2 for x, 2 times 2 is 4, plus 1 is 5. And so this would be 6 over 3, or 2. Here, I'm going to plug in 5 for x, so I'll get 25 plus 2 is 27. And then I'm going to plug in 3 for x. 3 times 3 is 9. 9 plus 2 is 11. And 27 minus 11 is 16 over 2 is 8. And then lastly, if I plug in 5, we get 2 to the 5th power. 2 to the 5th power is 32. Minus 1 is 31. Minus 2 to the 2nd power, 2 squared, is 4. Minus 1 is 3. So this would give me 28 divided by 3. I just realized I wrote this wrong, so this is wrong. This should be minus 2 as well. So this is over 3, therefore not a nice perfect even number there. But you'll get 5 and a third. Or 5.333. Okay. And then this last question says, which function has the greatest average rate of change then, and so that would be C, this one here, because 28 divided by 3 is going to be more than 5 1/3. We're looking at like 9 1/3. All right. Find the average rate of change of x equals -1 to x equals 2. So the denominator here will always be 3 for these as well, because we're looking at 2 minus a -1, and the distance between 2 and -1 on your number line is 3. So we're looking at a value difference of 3. And then we're looking at what are the outputs for that. So the output for this one at 2 is 6 minus -3. All right, so here the thing that you need to be the most careful about is that part of our formula is subtracting, and so we're doing 6 minus a -3. This is going to be 9/3, or 3. Here we're looking at 7 minus 1, so 6/3, this is 2. And here we're looking at 5 minus a -2, so you have to be careful with your sign here, which will give you 7/3, or 2 1/3. All right, so that is a little bit overview of your classwork. If you have any questions, you know how to reach out to me. Happy homeworking, and see you tomorrow.